Welcome to The Explainer. Today, we're diving into a gripping biological heist orchestrated by a completely microscopic invader. We're going to explore a parasite that literally turns your own cells against you, transforming them into a cozy home built entirely for its own survival. It's an incredible story that spans centuries, crossing all the way from historical autopsy rooms into the wild frontiers of modern hunting.
Okay, let's start with this fascinating medical mystery from the early 1800s. Picture this. You're at St. Bartholomew's Hospital in London. A curious first-year medical student named James Paget is watching surgeons perform an autopsy on a patient who had died of tuberculosis. But there was a really strange problem. The surgeons' scalpels kept getting incredibly dull whenever they tried to cut into the patient's diaphragm. Now, the surgeons casually dismissed it as a condition known as sandy diaphragm. But Paget, well, he wasn't satisfied with that explanation. So, when the surgeons went to lunch, he snuck back in, grabbed a piece of that gritty tissue, and rushed off to look at it under a microscope.
But here's where it gets wild. Unbeknownst to Paget, an intense rivalry was brewing. Someone else from that very same autopsy room had the exact same idea and took a sample to Richard Owen. Owen was the vaulted director of the British Museum of Natural History, the same guy famous for coining the word dinosaur. Both men looked at the tissue on the exact same day and discovered that the sand dulling those scalpels was actually thousands of tiny coiled worms. Owen rushed to publish the findings and claim all the credit, but Paget had actually written a letter to his brother that very day detailing his discovery, which secured his place in medical history as the co-discoverer of this bizarre parasite.
All right, let's get into Section 1, Anatomy of a Microscopic Invader. So, what makes this worm so incredibly resilient? The crucial point here is that unlike most parasitic nematodes you might have heard of, which rely on laying massive amounts of eggs, this worm is viviparous. This means it completely skips the vulnerable egg stage in the host's environment and unleashes live, moving offspring directly into the host's tissue. It's a highly aggressive reproductive strategy that ensures the next generation is ready to migrate the absolute second they're born. When you look at them, the physical difference between the sexes is honestly staggering, and it perfectly matches their roles. You've got the much smaller male, who possesses what are known as claspers, or a pseudobursa on his posterior end, which he uses to briefly attach to the female for mating. And then you have the massive female. She is nearly twice his size, and for a very good reason. Her entire body is essentially a factory, packed end-to-end with live embryos. They're just ready to be born.
Get this, a single female worm can pump out 1,500 to 2,000 of these live larvae into the host's body, and she does this continuously over a period of several weeks before the host's immune system finally catches on to what's happening and expels her. But by then, an absolute army has already been deployed inside you.
Moving right along to Section 2, the parasite's bizarre life cycle. The overarching life cycle of this parasite is highly unusual. The entire cycle, going from larva to adult and back to larva, happens within a single host. But there is a catch. The parasite faces a complete dead end unless it can jump to a new host. It manages this entirely via the food chain. An animal, whether it's a pig, a rat, or a human, absolutely must ingest the infected muscle tissue of another animal to keep the species from going extinct.
Let's break down how this hostile takeover happens step by step. It all starts the moment infected meat hits the harsh, acidic environment of the stomach. Ironically, the gastric juices and pepsin actually do the parasite a massive favor by dissolving the cyst around it, freeing the dormant larva. From there, the larva travels to the small intestine, burrows into the mucosal lining, and matures into an adult. They mate rapidly, and the newly born live larvae penetrate the intestinal wall to enter the host's bloodstream. They're basically using your circulatory system as a superhighway to reach the rest of the body.
And the timeline here is just brutal. This parasite holds a biological world record. It molts 4 times in just 36 hours to transform from a first-stage larva into a fully mature adult. Within a week, the males die off, their singular purpose fulfilled. Meanwhile, the newborn larvae find a host cell and take about 20 days to mature inside it. Once they hit maturity, they can sit dormant inside that muscle tissue for months, or literally even years, just waiting for the host to be eaten.
Now, this is the truly mind-blowing part about those 20 days of maturation. The larva randomly penetrates a striated skeletal muscle cell, like your bicep or your diaphragm. Once inside, it takes over the cell's machinery entirely. It physically transforms the human muscle cell into what biologists call a nurse cell. The parasite actually forces the host's body to build a brand new circulatory network, a capillary web around the cell, strictly to feed the worm and take away its waste. It's literally engineering its own customized life support pod right inside your muscle.
Which brings us to Section 3, Recognizing and Diagnosing Trichinosis.
Let's put this into perspective with a real-world scenario. Imagine it's June in Anchorage, Alaska. A healthy man in his 30s returns from a successful black bear hunt. But a week later, he's admitted to the hospital. He is highly anxious, his eyes are severely swollen, he's running a fever, and his muscles are in absolutely agonizing pain. He had experienced severe diarrhea a week prior, but thought he was over it. He had unknowingly ingested thousands of these microscopic invaders.
We can basically split his suffering and the disease of trichinosis into two distinct phases. First is the enteral phase, which causes that early gastrointestinal chaos like diarrhea and vomiting as the adult worms burrow into the intestine. But the real nightmare is the parenteral phase. This starts when the newborn larvae migrate through the tissues. This is what causes severe muscle pain, distinct bilateral periorbital edema, which is that intense eye swelling, and tiny bleeding events visible as splinter hemorrhages under the fingernails as the worms literally burst out of capillaries. The immune system also spikes a massive white blood cell response called eosinophilia.
Now, the larvae are blindly looking for skeletal muscle, but what happens if they take a wrong turn? If these wandering larvae accidentally burrow into cardiac tissue in the heart or into the brain, it can be catastrophic. Because they're in the wrong cell type, they can't form a nurse cell, so they just keep moving around causing immense tissue damage. This can lead to fatal myocarditis, meaning heart failure, or severe encephalitis, which is brain inflammation.
So, you might be wondering, how do doctors even figure this out? Well, making a diagnosis can be tricky. Looking for worms or eggs in a standard stool sample is completely ineffective. To definitively prove trichinosis, doctors must rely on a muscle biopsy, usually taking a small piece of the deltoid or calf muscle to physically see the encysted worm. They also use specific serological blood tests, but the catch is, those only turn positive about 2 weeks after the infection starts.
Let's wrap things up with Section 4, Treatment, Prevention, and Survival.
When it comes to medical treatment, timing is literally everything. If caught very early, administering antiparasitic drugs like albendazole or mebendazole can help eliminate the worms that are still in the digestive tract. But once the larvae have migrated and successfully encysted in the muscle, those drugs won't destroy them. At that point, doctors have to pivot to managing the host's extreme inflammatory response using powerful corticosteroids alongside strong analgesics to manage the severe muscle pain until the body adapts.
Since treatment gets so tricky later on, prevention is absolutely our best weapon. Thoroughly cooking meat to 160 degrees Fahrenheit is the easiest safeguard. But on a broader scale, we've largely eradicated this from commercial pork through legislation. Interestingly enough, laws were passed banning the feeding of raw garbage to pigs. Now, this wasn't actually done to stop Trichinella. It was enacted to stop a highly infectious virus called hog cholera. But inadvertently, cooking the pig's food completely eliminated the Trichinella cycle in commercial farms. Historically, communities also used a device called a trichinoscopy, essentially projecting a compressed slice of pig diaphragm onto a screen to visually inspect for the cysts before the meat was ever sold.
Now you might be thinking, I'll just freeze the meat. Well, think again. While standard freezing can kill the worms in domestic pork, wild animals, like the bear from our Alaska vignette, possess a natural antifreeze molecule. This protects ice crystals from forming inside the nurse cells during those harsh winters. That means this antifreeze protects the parasite just as well as it protects the animal. Freezing wild game meat does absolutely nothing to make it safe.
And that brings us to the end of this explainer. We've seen how a microscopic worm can hijack your very cells and rewrite your circulatory system, all while hiding silently in the food chain. It leaves us with a pretty provocative thought. Knowing that wild game could be harboring an antifreeze-protected, muscle-hijacking parasite, how closely will you be looking at your next medium-rare steak?